Bismillahirrahmanirrahim. Assalamu alaikum. Today we have lecture 3 of the discrete structures, CSC 102. In the previous lecture we have studied logical equivalences, De Morgan laws, tautologies and contradictions, and we have also studied laws of logic, and we have studied some examples in which we can prove logical equivalences by using truth tables and laws of logic. Today we will study conditional propositions, their negation, inverse and converse. I shall give you some examples in which we show how we interpret the conditional statements, and then we shall study contraposition, biconditional statements, and then we shall interpret necessary and sufficient conditions in the conditional statements, and at the end we shall repeat the logical equivalence in which the conditional statements will be involved. Now let's start conditional statements. By definition, if we have two propositions, then the conditional proposition or conditional statement is denoted by P implies Q, for example like this here, and we read it as if P then Q. It is written as here, or we read it as P implies Q. And this conditional statement is false when P is true and Q is false. In fact, in this conditional statement, P is said to be the proposition, hypothesis, and Q is said to be conclusion. The conclusion is based on the hypothesis. If the hypothesis is true and the conclusion is false, then we say that this conditional statement is false. Otherwise, this conditional statement is true. For example, if you work hard, then you will succeed. In this statement there is a condition. What is the condition? If you work hard. So this is your hypothesis. And what is the conclusion? You will succeed. Now the conclusion depends on the hypothesis. If hypothesis is true, then conclusion is true. Then this conditional statement is true. If hypothesis is false, if you do not work hard and you succeed, then this logical statement or conditional proposition will be false. And this example, if John lives in Islamabad, then he lives in Pakistan. The hypothesis in this conditional proposition is this: if John lives in Islamabad, then obviously he lives in Pakistan. If this conclusion is false, this conclusion is true, sorry. If John lives really in Islamabad, then he lives in Pakistan. Then this conditional statement is true. But if we say that if John lives in Islamabad but he doesn't live in Pakistan, then this conditional statement will be false. There are other possibilities here. If we say that if John doesn't live in Islamabad and John doesn't live in Pakistan, then this conditional statement is also true, because hypothesis is false and the conclusion is false. in this case the conditional proposition will also be true. But if we say that if John doesn't live in Islamabad and we say that he lives in Pakistan, then again this conditional statement will be true. If John doesn't live in Islamabad, he may live in Peshawar, Rawalpindi or any other city of Pakistan. Again this conditional statement in this case will be true. The truth table of the conditional proposition if then is this. If we have two propositions P and Q, then the possibilities of the truth values of P and Q is true, true, false, false, and true, false, true, false. The conditional statement, or it is also said to be implication, P implies Q. P implies Q, then we can see that if P is true and Q is true, then this conditional statement P implies Q is true. If P is true and Q is false, as I told you, if hypothesis is true but the conclusion is false, then this conditional statement P implies Q is false. This is the only case where this conditional statement is false, when the hypothesis is true and conclusion is false. If we say that the hypothesis, which is P, is false and the conclusion is true, then this conditional statement is true. As I have told you in the previous example, if John doesn't live in Islamabad, then he lives in Pakistan. Then the hypothesis here is wrong and the conclusion he lives in Pakistan is true. As I told you, if John doesn't live in Islamabad, then he may live in Rawalpindi, Islamabad, Karachi. Then again, even then he lives in Pakistan. So this conditional statement is true if hypothesis is false but the conclusion is true. In the next case, when hypothesis is false and conclusion is false, means if John doesn't live in Islamabad, he doesn't live in Pakistan. Both hypothesis and conclusions are wrong. In this case, the implication or conditional statement is also true. Now I shall give you some other forms of conditional statements we encounter in daily life examples, which are exactly same as conditional statement, but their interpretation is different. For example, if we say that the online user is sent a notification of a link error if the network link is down. If someone is using internet or computer, then the online user is sent a notification of a link error, that there is a error in the link if the network link is down. Now this statement is also a conditional statement. What is the condition here, or what is the hypothesis? The network link is down is the hypothesis or the condition in this statement. So the above statement can be written as, if the network link is down, then the online user is sent a notification of a link error. If we say that this is a proposition, the network link is down and the online user is sent a notification of a link error. If we say the first proposition as P, the network link is down, and Q, the second proposition, which is the conclusion, the online user is sent a notification of a link error, then this conditional statement can be written as, if P then Q, or P implies Q. the above statement or the given statement is of the form Q. This statement is of the form Q if P. So this is another form of conditional statement. If we have a statement of this form Q if P, means the online user is sent a notification of a link error if the network link is down, because the hypothesis is given at the end after if, and the conclusion is given at the start in this statement. So if we have a statement like this is also a conditional statement which is of the form Q if P. We can write it as if P then Q. So another example of the conditional statement, that this is when you study the theory. So this is the condition here. When you study the theory, you understand the material or exercises or questions. If you study the theory, then you understand the questions or exercises or material. This statement is also a conditional statement. This statement can be written as if you study the theory, then you understand the material. So what is the condition or hypothesis in this conditional statement? You study the theory, this is the hypothesis, and what is the conclusion? You understand the material. So this is the conclusion. So we conclude here that if we are given a statement like this, when you study the theory, when here is used as if. So the above statement can be written as here, if you study the theory, then you understand the material. So if you take P as you study the theory and Q as you understand the material, then the statement becomes P implies Q, or this if P then Q. The form of the given statement is written here when P comma Q. So if we have a statement like this, which is when P comma Q. So this statement or a statement like this is also a conditional statement where when is used in place of if, and comma Q means then Q. So we have conditional statements of this form also, which can be rewritten in the form if P then Q, or P implies Q. Another example, studying the theory is sufficient for solving the exercise. So this is somewhat same example, but it is written in the different manner. So there is a condition also in this statement. Studying the theory is the hypothesis, is the condition in this statement, is sufficient for solving the exercise. So what is the form of the conditional statement which is used here? The form of this statement is P is sufficient for Q. Means if we say that this is a P, studying the theory is the hypothesis, is the condition in this conditional statement, and solving the exercise, this is the conclusion. Solving the exercise is the conclusion in this example. So this statement can be rewritten as if you study the theory, then you can solve the exercise. So this is another form of the conditional statement, so which is equivalent to the P if P then Q. If we take P, you study the theory, and Q be a proposition which is you can solve the exercise, then the above statement can be written as if P then Q, or P implies Q. So there are many other forms of the conditional statements. For example, or you can consult or see in the book of Discrete Mathematics written by Kenneth Rosen, there are several forms of conditional statements are given on page. For example, if we see the book of Rosen, Discrete Mathematics, here on page 6, the form of conditional statements are given. For example, they have given, I write some of the forms, but I recommend you to see the book page 6 of the Discrete Mathematics by Kenneth H. Rosen. They have given, he has given Q when P, so this is also an equivalent form of conditional statement. Another is given Q whenever P, this is also another form of the conditional statement. Q follows from P, this is also another form of the conditional statement. P only if Q, this is also another form of the conditional statement. There are many other forms of the conditional statements are given, you may see in the book. I have given some more examples of the conditional statements. If P and Q are statements, then P only if Q means if P then Q. For example, John will break the world's record for the mile run only if he runs the mile in under 4 minutes. So this is equivalent to, if John breaks the world's record, then he will have to run the mile in under 4 minutes. So we can write the equivalent form of conditional statements in the form if P then Q. Here, if, this is the proposition P, if we suppose, and this is the proposition Q, then the above statement can be written in the form if P then Q, or P implies Q. The next, we study some equivalent form of the conditional statements which are equivalent to not P. P implies Q here is equivalent to not P or Q. So how we can prove that P implies Q is equivalent to not P or Q? The simplest way to prove these two statements to be equivalent is using truth tables. So we construct truth table for P implies Q is equivalent to or not P or Q. Another another activity is that what is the negation of the conditional statement? Means here you know this is the sign of not or negation. So negation of P implies Q, this is equivalent to P and not Q. So we will prove these two statements, or compound propositions to be equivalent. We shall prove these two by using truth tables, which is the easiest way to prove two statements equivalent. We construct the truth table of these two expressions. This is the truth table of P implication Q and the other compound statements. We have P and Q, two propositions. The truth values are true, true, false, false, and true, false, true, false. the P implication Q, as you know, the truth table of P implication Q are true, false, true and true. Now we need not P or Q. This statement, we have to now prove P implication Q is logically equivalent to not P or Q. So we have to construct the truth tables of truth values of not P or Q. So if we write not P here, so not P is the negation of P. The negation of P, the truth values of negation of P will be opposite to the truth values of this P. If P is true, not P is false. Again, P is true, not P is false. P is false, then not P is true, and P is false, not P is true. Now we take not P or Q. We need two columns, Q and this not P. So we take the disjunction of not P and or Q. So not P or Q will be, we know that the disjunction of two proposition is true if at least one of two proposition is true. Means either P or Q is true, then the disjunction of not P and Q will be true. So here Q is true, not P is false, therefore here we have true. Again we have false, false. The truth value of not P or Q is false. Next we have true here and true here, so the truth value will be true. Next we have false here and we have true here, so the truth value will be true. So now we can see that P implies Q, or if P then Q, is logically equivalent to not P or Q, because all the truth values of P implication Q are exactly equivalent to the truth value of not P or Q. In the first row we have true, true, second row false, false, true, true and true, true. As the truth values of these two compound propositions are exactly same, therefore these two compound propositions are logically equivalent, and we write it as P implication Q is logically equivalent to not P or Q. Similarly, the other statement, this not P implication Q is logically equivalent to P and not Q. Now we need not P implication Q, which is the opposite of this. Here we have true, here we have false, here we have false, here we have true, here we have true, here we have false, true and false. So this is the negation of P implication Q. Now we have to construct P and not Q. To construct P and not Q, we need not Q. So if we construct the truth value of not Q here, not Q, so we know that Q is in the first column, it is true, so not Q is false, then true, then false and then true. Now we need P and not Q, so we need this column and this column P. Here we have false, true, and here we have false, so we have conjunction operator. Here we have obviously false, here we have true, here we have false, because this is not Q is false and P is false. Here again P is false and not Q is true, so we have false here. Now we can see that the truth values in this column are exactly same as the truth values in this column. So these two compound propositions, this and this, have exactly the same truth values. So these two compound propositions are logically equivalent. So these two statements are actually the equivalent to not P implies Q is logically equivalent to not P or Q, and the other is P and not Q. This shows that the conditional statements or negation of conditional statement can be written in the form of simple operators, which are and, not, and negation operators. The next, we see some examples how we negate the conditional statements. For example, if this is the proposition, given proposition, if my car is in a repair shop, then I cannot get the class. So this is a conditional statement. What is the hypothesis? My car is in a repair shop, and the conclusion is I cannot get the class. So what will be the negation? Because this is a conditional statement which can be written as if P then Q, or it can be written as P implies Q. And we know that what is the negation of this P implication? Not P implies Q. This is equivalent to, logically equivalent to P and not Q, as we have proved in the previous slide. So how we can write its negation? Its negation is actually P and not Q. So what is P? Here P, my car is in repair shop, it will come here. This is P, and there is a AND operator between these two propositions. Here we have AND what is the negation of Q? Not Q. Means Q is what? I cannot get the class. The negation of this will be I can get the class. So the negation of this conditional proposition, this is can be written as my car is in the repair shop and I can get the class. So this is the opposite statement. Another proposition, how can we negate it? If Sarah lives in Athens, then she lives in Greece, as Athens is the capital of Greece. So what is the hypothesis here? This is the hypothesis. We can say it P. Here we have then, and she lives in Greece. What is this? This is the conclusion. This is Q. So this statement is actually P implies Q. So what will be the negation? P will come same as Sarah lives in Athens, and there is a AND operator here, as we have seen that in the negation of P implies Q, this we have P and not Q. So the negation of Q is actually she doesn't live in Greece. So this is the negation of conditional statement. Next, we shall see the converse and inverse of conditional statements. So what is the converse of the conditional statement? Suppose a conditional statement of the form if P then Q is given, then its converse can be written as if Q then P. So its converse, we reverse the statement. If we have if P then Q, means P implies Q. Now what is the converse of this statement? The converse is Q implies P. So this is the converse of conditional statement P implies Q. And what is the inverse of this statement P implies Q? The inverse can be written as not P implies not Q. So this is the inverse. In converse, we replace the position of P and Q, and in inverse we take their negations. For example, here we have P implies Q. In inverse we take not P implies not Q. So this is inverse of P implies Q. Symbolically we can write it as I have written here. The inverse can be written as not P implies Q. So we can take same example. For example, here as we have written, if my car is in repair shop, then I cannot get the class. If we want to write its converse, how we write it? If I cannot get the class, then my car is in repair shop. So this will be the converse of the given statement, this proposition. And what will be the inverse? In inverse, as I told you, we take the negation of P and Q both. So inverse of this statement, if my car is in the repair shop, then I cannot get the class. The inverse will be, if my car is not in the repair shop, then I can get the class. Because we are writing the negation of I cannot get the class is I can get the class. I repeat, the inverse of this statement is, if my car is not in the repair shop, then I can get the class. So I hope you understand how we write converse and inverse of conditional statement P implies Q. Here some other examples, that the converse is not equivalent to the given conditional proposition. So there is a note here that the converse of a conditional statement and the conditional statement itself are not logically equivalent. So for example, if John is from Chicago, then John is from Illinois is true, but the converse, if John is from Illinois, then John is from Chicago, may be false. You can interpret this conditional statement yourself, as I have given you the example of, if Sarah lives in Islamabad, then she lives in Pakistan. This is the same conditional statement. If we take the converse of conditional statement, then these two statements, P implies Q and the other is Q implies P, these two statements are not logically equivalent. Similarly, another example here, if an object is triangle, then it is a polygon. It is not equivalent to, if an object is not a triangle, then it is not a polygon. It may be false. So it can be a polygon, because square is also a polygon. So you can interpret yourself these conditional statements, that the converse and inverse of the conditional statement are not logically equivalent to P implies Q. The next is contraposition. How we write the contraposition or contrapositive of a conditional statement. The contrapositive or contraposition of a conditional proposition of the form if P then Q is, if not Q then not P. So this is different from inverse. Please note that in converse we write, if we have P implies Q, the converse is Q implies P, and the inverse is not P implies not Q. So here the contraposition of a conditional statement P implies Q, this is written as not Q implies not P. So this is different from inverse. So don't mix up the inverse and contraposition of conditional statements. So we can see the difference between converse and the contraposition of conditional statements. So here in inverse we have not P implies not Q, but in contraposition we have not Q implies not P. So symbolically this is written as this. For example, if today is Sunday, then tomorrow is Monday. What is the contraposition or contrapositive of this statement? This statement is actually P implies Q. What is P here? P is today is Sunday. This is the hypothesis, and what is the conclusion? Tomorrow is Monday. If we take P as today is Sunday and Q as tomorrow is Monday, then we can write contrapositive of this conditional statement as not Q implies not P. It means if tomorrow is not Monday, so this is the negation of Q, then negation of P, today is not Sunday. So this is the contraposition of the equivalent statement, conditional statement, P implies Q. One more thing, that I have told you that converse and inverse of conditional statement P and P implies Q, these two are not logically equivalent to each other. Means P implies Q is not logically equivalent to Q implies P, and also not logically equivalent to not P implies not Q. But in contraposition, the contrapositive of a conditional statement is logically equivalent to its conditional form P implies Q. That is, if we have P implies Q, then its contrapositive is logically equivalent to this statement, not Q implies not P. So once again, a contraposition of a conditional statement is logically equivalent to P implies Q. So we can write it as, the next is biconditional. So the definition of biconditional is given by, if we have two propositions P and Q, then biconditional of P and Q is denoted by, as you can see here, P if and only if Q, and in symbols or in logic it is written as P if and only if Q. So in conditional statement we have seen that we write P implies Q as P implies Q, but in biconditional we have a double arrow P this Q. So this is basically a biconditional statement. Biconditional means these two P and Q are the conditions for both. We'll see by examples how. This biconditional statement or biconditional proposition, it is true when both P and Q have same truth values. That is, if P is either P is true, and if P is true and Q is true, then biconditional of P and Q is true. And the second case is if P is false and Q is false, then P biconditional Q will be true. In two other cases in which either P is false or Q is false, then this biconditional statement will be false. For example, if we see the truth table here of biconditional, it can be written as, if we have P and Q, two compound proposition, the truth values of P are given by this and truth values of Q are given by this. Now the P biconditional Q, or we read it as P if and only if Q. If P is true and Q is true, then it is true. The other two cases in which either P is true or P is false and Q is false or Q is true, in this case the biconditional of P and Q is false. And in the last case, when P is false and Q is false, this is true. Now see the previous example here. This computer program is correct if and only if it can be written as this. If and only if, here I have written if and only if can be abbreviated as IFF, and it is read as again if and only if. So this computer program is correct if and only if it produces the correct answer for all possible set of input data. So you can see that here if we take P, this computer program is correct, and Q as it produces correct answer for all possible set of input data. So the condition is on both P and Q. If computer program is correct, then it will give true values, and we can see that if a computer program give us true values, correct answer for all possible set of input data, then this computer program will be correct. So here we have a biconditional, means P is condition for Q and Q is condition for P. In this case, we can write P implies Q, means P is condition for Q, and Q is a condition for P. So biconditional of P and Q is logically equivalent to P implies Q and Q implies P. So it's truth table. By using truth table, we can see that P implies Q, so P biconditional Q here is logically equivalent to P implies Q and Q implies P, as we can see that the truth values in this column and in this column are exactly same. So we can see that we can say that P biconditional Q is logically equivalent to the P implies Q and Q implies P. So in biconditional propositions, there is a condition on both the propositions. If P is true, then Q is true. The next is how we interpret the necessary and sufficient conditions in logical statements or conditional statements. For example, if we have this proposition, if a number is divisible by 10, then it is divisible by 2. So what is the hypothesis here? If a number is divisible by 10, then hypothesis is a number is divisible by 10. So as I have written, it's called a hypothesis, I have told you earlier. And what is the conclusion? Then that number will be divisible by 2. So this is conclusion. So when the if-then sentence is true, we say that hypothesis is a sufficient condition for the conclusion. Yes. If the hypothesis is true, or if this statement as a whole is true, then we say that hypothesis is sufficient condition for the conclusion. Or as I have told you that we can write P is sufficient for Q. P is sufficient for Q. Means this is hypothesis. Hypothesis is sufficient condition for the conclusion. And the conclusion is then called a necessary condition of that hypothesis. For if a number is divisible by 10, it is necessarily follows that it is divisible by 2. So in this case, the conclusion means Q is necessary for P. So in such statements or conditional statements, if hypothesis then conclusion, then hypothesis is sufficient condition for conclusion, and the conclusion Q, or Q is the necessary condition for the hypothesis. So this is how we interpret the necessary and sufficient condition. We see another example here. Consider the logical or conditional proposition: if John is eligible to vote, then he is at least 18-year-old. So if we take P, John is eligible to vote, and Q as he is at least 18-year-old, then what is hypothesis? This is P is hypothesis and Q is the conclusion. If someone say if John is eligible to vote, then it is sufficient for this that he is at least 18-year-old, because at least 18-year-old or 18-year age is the necessary condition to be eligible for vote for anybody. So we can say here that P is the sufficient condition for Q, but Q is the necessary condition for P, because if John is not 18-year-old, if he is less than 18-year-old, then he is not eligible to vote. So P is sufficient for Q, but Q is necessary condition for P. So the truth here, you can say that the truth of the condition John is eligible to vote is sufficient to ensure the truth of the condition John is at least 18-year-old. In addition, the condition here John is at least 18-year-old is basically the necessary condition for John to be eligible to give a vote. So this is how we interpret the necessary and sufficient condition in these conditional propositions. The next is, if we take two propositions R and S, how we write these necessary and sufficient conditions R and S. If we have two propositions, then if we have R is sufficient condition for S, it means if R then S. But if we say R is necessary condition for S, then we write it as if not R then not S, or we can write it as if not R implies not S. This is basically necessary. In necessary condition R implies S, and this is the sufficient condition, and in case of necessary condition we write it as. And if we have R is necessary and sufficient condition for S, if we have both conditions, R is necessary as well as sufficient condition for S, then we say that R if and only if S. In this case we have bicondition, means there is a condition on R and S as well. In this case we write R if and only if S. So R is necessary and sufficient condition for S is equivalent to a biconditional of R and S. Next I shall give you an example of two compound propositions, how to prove them equivalent, which involve conditional statements or conditional propositions. In the previous lecture we have proved two compound propositions to be logically equivalent using logic laws. This is the same example, but it involves the conditional statements. We prove these two compound propositions using the same way as we have proved two compound propositions to be logically equivalent in the previous lecture. So we take the left hand side equal to this is the left hand side. So we shall prove this compound proposition to be logically equivalent to this right hand side compound proposition. So first of all we can see that we have not of the whole expression, negation of the whole expression. We shall apply the negation law. Negation, it will come negation of R. Here we have disjunction operator, it will be converted into the conjunction operator, and we have applied not on the rest of this expression. What we have used here, we have used the De Morgan law, and you know in De Morgan law we have negation of P or Q. This is logically equivalent to negation of P or will be converted to and negation of Q. So we have applied the De Morgan's law here. The next, we have applied here the negation. The negation of Q and not R implies not P. So now we have, in fact, we have simplified this conditional statement. This P implies Q. This can be written as how, if we have P implies Q, we have seen in the previous slides that this is logically equivalent to what? Not P or Q. So not R implies not P. This will be logically equivalent to not of not R, and this implication will be converted to or as here, and not P will remain same. Here we have not of not R, so we can apply here double negation law, which is not of not P. This is basically equivalent to P. So here not of not R becomes R, and the rest of the things are same. Now here we can apply now the negation or De Morgan law. Here we have negation of Q and this expression. By using De Morgan's law, we can write not Q, this conjunction operator will be converted to disjunction here, and we apply not here using De Morgan's law. Again we apply the De Morgan's law here on this expression, not R, this disjunction operator will be converted to conjunction operator, and we have here not of not P. Here again we shall apply the double negation law and we shall obtain P. So here now we have not or and not Q or not R and P. So we can apply here the distributive law. As we have not R here and not R here, so using distributive law, not R and not Q, and in the middle we have disjunction operator, and we have not R and this expression, this whole expression, not R and P. So we have applied the distributive law here in this step, and then associative law, not R and not Q, or we have not R here. We can interchange here the place of not R and this using associative law. We can write it as this. Now we have not R and not R, so this is basically P and P. This is logically equivalent to P. We have seen in the rules of logic or logic laws that P and P is logically equivalent to P. So we can write not R and not R as not R, and we have P here. Now we can apply again the distributive law here, not R and not Q or not R and P. So using distributive law we can write this statement equivalent to this, not R and not Q or P. So now we have to replace this by using commutative law, and we get the right hand side. This is basically the right hand side. So the left hand side is logically equivalent to the right hand side. We have proved it using the some laws of logic. The next, at the end, we shall study how to convert some simple English sentences into logical form. So the conversion of statements into symbols. If we have these three propositions, if we suppose V is a proposition, the user enters a valid password, A is access is granted to the user, and C is the user has contacted the network administrator. So by using these three propositions, we shall write some statements into symbol forms. For example, if we have this statement, the user has contacted the network administrator but does not enter a valid password. So the user has contacted the network administrator. So what is this? This is the proposition C. This here we have but is basically connective. I have told you that but is usually used as AND operator. So but does not enter a valid password. Does not, basically this is the negation of this statement V. If we have V, the user enters a valid password. What is the negation? The user doesn't enter a valid password. So how can we write this statement into logical form or symbols? So first we have C, but is used as AND operator, and we write here disjunction conjunction operator, and we have negation of V, that the user doesn't enter a valid password. So this statement, this sentence, or you can say that sentence, can be written in the symbols form like this: C and not V. So the preference here is basically we can write here not V. Not has a preference over the conjunction operator, so not will be applied first on the V, and then we take the conjunction of V, C and not V. Another example, access is this there is a second sentence, or you can say statement: access is granted whenever. So whenever is basically here a connective. I have told you that if we have used or whenever is used for if. Whenever is usually used for the if in the sentences or English sentences, you can say that. So access is granted whenever the user has contacted the network administrator. So there is another connective here. We have or enters a valid password. So we have three statements here connected by two connectives, logical connectives. Here we have if, here we have or. So I have told you there is another form of conditional statement, Q whenever P. So this is basically logically equivalent to if P then Q, or P implies Q. So here we have Q, not Q. Access is granted is basically A. This is proposition A, access is granted to the user. So here we have, this is basically access is granted. This is proposition A. We have A here. Whenever is used for if the user has contacted the network administrator. We have another statement. This is what? This is basically C. The user has contacted the network administrator. So this statement is basically C. So we have C here, and we have another connective here, or enters a valid, user enters a valid password. What is this? This is basically V. So we can write this whole statement as A whenever C or V. So whenever here is basically used as if, as I have told you here, Q whenever P is logically equivalent to basically if P then Q, or P implies Q. So here we have a statement A whenever C or V. So I have told you that the or disjunction operator has a preference over the implication operator. So we can write this in bracket, and this expression is logically equivalent to basically C or V implies A. So the whole statement, the given statement, this is written in symbolic form as. So to write the statements in English into the symbol forms, first you have to locate the connectives between statements. So in this statement, what are the connectives which connects the propositions or statements? Here we have a connective, and here we have a connector, and then you relate the propositions using the logical connectives and other forms of the symbols. Another example is given this: access is denied. Access is denied, basically the negation of access is granted. So we have one proposition here which is the negation of A. Here we have not A, and we have logical connective if here. Another statement: the user has not entered a valid password. So here we have another negation of a statement, which is the negation of C. This is basically the negation of C. And next we have a logical connective, or has not contacted the network administrator. Here we have again the negation of a statement, which is the negation of basically negation of C. I think this is basically the negation of C, and this is the negation of V. This is basically the negation of V. So now we write it in simplified form: not A, and we have if, and then not V, and we have or here, or, and then again not C. So now we know that or has a preference over the if or conditional statements or implication. I have told you that the preference will be taken as, first we take negation operator, then conjunction, disjunction, and then the implication and biconditional. So this is the order of preference of the logical connectives. So here we have not V or not C. So, and here we have form not A if, and we have this expression. So this is basically another form of conditional statement. I have told you Q if P is basically the form of a conditional statement. If we have Q if P, then this is logically equivalent to basically P implies Q, or if P then Q. So this statement in symbols can be written as, here we have not V or not C. We can write not V the disjunction operator or not C and implies not A. So the whole statement, this can be written in the form of symbols or in the form of logical connectives as. We take another example. For example, this, if we are given a statement, whenever the file is locked or the system is in executive clearance mode, the user cannot make changes in the data. So if we take here whenever as if the file is locked, another proposition, there is a logical connective, or the system is in executive clearance mode, this is another basically statement, the user cannot make changes in the data, this is another statement. So we have three statements basically in this sentence. Whenever will be used as if, I have told you. If we take the file is locked as L, E, the system is in executive clearance mode, and U as a proposition, the user can make changes in the data. Here we have cannot, but we can write here the negation of U. Here U can be taken as the user can make changes in the data. So here we will have negation. So this whole statement can be written as this, because this is the form of conditional statement if P, Q. This can be written as so, and here we have if this whole statement will be P, and here this is basically the Q, but in P we have P, basically P is basically the disjunction of two propositions L or E. So we have L or E and implication U, not U basically. So we can write this statement in the symbol form as. So till today we'll stop here, and the lecture summary of today's lecture is we have studied conditional propositions, and we have studied also their negation, inverse and converse by watching some examples. We have studied also the contraposition of conditional statements, and next we have studied biconditional and the interpreting necessary and sufficient conditions, and at the end we have seen some examples in which we have translated some English sentences into logical forms or in the form of symbols. Thank you very much. Allah Hafiz.